Good noon, everyone. Thank you for joining this today's webinar and having huge participation for my webinar today's. Today, I'll be talking about the general discussion on the combinational logic circuits. The outline for today's session is combinational logic circuit concepts, then circuit implementation of SOP and QoS, how to synthesize them, generalized idea about or generalized form of the SOP and POS, how to implement these designs, how to do scalable design, what are the scales of integration, and then I'll talk about the digital chip design flow and HDL differences between Verilog and VHDL and different design abstraction levels. Finally, I will conclude my topic with Verilog code and test bench in Verilog. So I'll be just giving you brief outline of all these topics, and many other things are covered in the given book. Okay. In general, combinational logic, whenever we see there are one or more than one input and one or more than outputs are also available. And the requirement is that any change at the input side happens, immediately it will be processed and it will processed data will be reflected at the output. So what does this infer? The implication is that driver is always required. Okay, if the circuit is not having any driver, you won't get any output. So this is very important concept while writing test Verilog codes. The generalized combinational logic circuit, when we say there are n number of inputs and m outputs. So with respect to n inputs, there will be 2 to the power n number of rows in a matrix. Okay, that is a truth table, what we call. And when there are n outputs, then the total column will be, number of columns will be n plus m. Okay, and the length of the matrix will be 2 to the power n. So what happens when we are writing it in the truth table format, we will be able to write 2 to the power 2n number of functions. So this is how it is, what I mean to say. So when there are n inputs, 2 to the power n number of rows will be there, and corresponding to each output bit pattern, there will be 2 to the power n number of possible functions. So total number of functions which we will be able to write is 2 to the power 2n. Okay. So your circuit will be very, very generic. Now, when we want to implement such kind of circuits, we do have different ways. The first way is to write a truth table and take a simple, I am taking a simple circuit here wherein the output is going high for truth table entry is equal to 1, then 3, and then 6. So when we are writing output is equal to 1, what is expected is that to generate output 1, the input pattern should be generated such that the output bit is equal to 1. So in the first case, when A is 0, we have to turn it into 1. So we will write A bar. When the input B is 0, it is turned 1 and C is already 1. So nothing is to be done. And the product of these, when we take all the all the terms, then the output P is equal to 1. So it means that this mean term, this is called as a mean term, and mean term M1 is equal to 1. So if we write it in this way, then naturally what we will be getting is that the circuit is function of three input variables A, B, C. Sometimes these variables are also called as literals. Okay, and the summation of these mean terms is 1. So when we write it in the form of literals and the canonical, standard canonical form, it is represented as A bar B bar C plus A bar B C plus A B C. And if we map this circuit, then directly we will get three AND gates, three input AND gates, M1, M3, M6 corresponding to the minterm, and the outputs are then summed so that P truth table, given truth table output, that is column P, we will be able to generate. So when we are building this kind of circuit, we call it as a sum of products. So we are calling it from the reverse way. We are traversing from the output to the input. So sum of product. Okay. Then when we are trying to, let's say there is another possibility which exists, that A, B, C, these are three terms again, and I am taking another vector, say Q, and Q is equal to, now again some entries will be 1 and other will be 0. Okay, so now let us take the entries which were left out from the previous table, that is P is equal to 0 is marked here as a Q. Okay, so the here what we are trying to do is that output is equal to 0. So what we will do is we'll try to add these variables logically arraying. Okay, so then it is called as a max term, and we represent it as, in the first case, M0, it's nothing but A plus B plus C. But this plus is nothing but logical operation, Boolean operation. Okay, so it is ORing. So if we want to do all this summation, okay, so all these max term products, max terms will be done. Finally, on the max terms, we will be operating and. Okay, so what we call this as a product of sum. So the first, what we are doing, the first operation is summation, and finally we are doing product. So product is nothing but AND gate. So while calling this kind of Boolean expression or logical expression, we call it as a product of sum. So when we are writing all the literals for a given term, then we call it as a standard canonical form. Okay, and now what I want to highlight here is that if you look at the previous implementation, in that case we were requiring three AND gates, three input, and one OR gate. Okay, so this is two stages. First stage is AND gate, second stage is OR gate. But in the next implementation of the same expression, what is the requirement? 5 OR gates of 3 input and one AND gate with 5 input. So this is another way to realize the expression. But now remember that Q is equal to invert of P. Okay, so this point must be considered very well while designing your circuit. Okay, now let's look at the another possibilities. Okay, so when we have a standard canonical format, expression in standard canonical format, it can be SOP or it can be POS, then we can apply De Morgan's theorem, and applying De Morgan's theorem we can synthesize the given network in the four different possible forms. If our circuit is SOP expression, then AND OR stage, this circuit can be implemented using by just applying De Morgan's theorem into NAND functionality. But if you apply De Morgan's again on this NAND expression, we will get the expression, the same expression, which can be realized using OR NAND functionality. So in this case, the first stage is OR gates and the second stage is NAND gate. Now, if you do again De Morgan's on this expression, then we will be able to transfer this circuit from NOR or technology. So the NOR is the first stage and OR is the second stage. So all these are two-stage circuits, but by applying De Morgan's repetitively, we can transfer this circuit from AND OR to NAND NAND or NAND NAND to OR AND to NOR OR and NOR OR to AND OR. And the cycle repeats. If you repetitively do this, then the synthesis of the circuit will remain in these four types of circuits only. Okay, so depending on availability of our logic gates which are available with us, we can decide in which technology to map the given expression. Same is the case with the POS expression. If we want to translate OR and circuit, by applying De Morgan's, we can convert it into NOR-NOR circuit, or from NOR-NOR circuit, we can convert it into AND-OR form, AND-NOR format. AND-NOR format, again apply De Morgan's theorem, and we can convert it into NAND AND format. Okay, so there exist these four possibilities. Okay, there are many others. We'll discuss it little later. Okay, so uh, in general, when I want to write as a generic or generalized format, so as I have stated, there can be 2 to the power 2n number of possible expressions. So what is possible? We can write min terms and max terms for all the variables as shown in the table. Okay, so all min terms are represented using small m and suffix letter corresponding to its row, and max terms are represented using capital M and suffix corresponding to its particular row. And let us take a generalized expression, output expression F, and the outputs are y0 to marked as y0 to y7 corresponding to each row. So now let us say I don't know what is the function. Okay, because there are 256 possible functions which can be generated with three number of input variables. Okay, so what is going to happen? The function in generalized format, if I want to write, I can write the output expression is f is function of three input variables a, b and c, and we can equate it is equal to y0 m0. So y0 is the whatever is the function value in the first row. It can be 0 or it can be 1, and then corresponding to its min term m0. So if y0 is equal to 1, then y0 times the min term is nothing but one product of one dot with a bar, b bar, c bar. So finally output will be a bar, b bar, c bar. And we can add all such n number of terms whatever are there. So in this expression there are 8. So we can say y0 m0 plus y1 m1 plus y2 m2 till y7 m7. So it is nothing but a sum of product format, right? So in mathematical format, if I have to write, how can we represent? It is a function. Output expression is function of three variables or three literals called as A, B and C, and we can represent it using summation I 0 to n. So this n can be number of last row in your truth table. So in this case, it is 7. So 0 to 7. So covering all the possibilities. And then we can simply write that yi product mi. So this becomes a generalized format. So now you can write all 256 expressions in this way. And then you can say that f0 is function like this, f1 is function like this, f2 is function like this, and so on. Okay. Now, if I have to represent the given expression in terms of, let's say, max term, what should be the generalized way? In max terms, our expectation is function is ABC is going to produce output is equal to 0. Okay, so what we need to do? Y0 plus M0. Max term we have to add, and then product of all these add all terms we have to take because it is a product of sum expression. So we will write sum and sum of all the terms, sum of every max term product. Finally, we are going to do product. Okay, so A0, B0, C0 plus if Y0 is equal to 0, then that term will be equal to 0. If Y1 is equal to, let's say, 1, and then summation of M1 is not going to affect because output is going to be 1 for this particular term. So what will happen? Out of this n number of terms, if any term is 0, ultimately we are going to get output is equal to 0. It may happen that 1 0 0 0 0, so 1 1 1 1 and 0. So at a time only one particular set of inputs we are going to apply, and hence a particular term will be 0 and others will be 1. Okay, so product will be corresponding to the given row. Okay, so we can represent it in mathematical format. Function a is equal to product of I starting from 0 to 7, and we can then say yi plus mi. So depending on the number of rows, we can represent this I is equal to 0 to n. Okay, so this is a very generalized format. Now again using this we can write 2 to the power 2n. That is, in this example there will be 256 such functions. So one can write it all these functions. Okay. Now what are the different ways to specify your design? Okay, so I am considering this as a black box, and there will be some inputs, some outputs. Okay, so the first way to specify your circuit is writing a word problem. Say for example, design a circuit to perform addition of two single bit numbers. So this is a word problem. Now we need to understand the requirement of the circuit, what are the inputs, what are the outputs, and then write the expressions for this black box and design the black box. So the goal of our course is to design such black box after understanding the basic components. Okay, so usually in practice, in commercial products, if you look at, all the specifications are given in word problem. Very rarely it comes in terms of algorithms. Okay, so we need to understand what are the expressions, and how to get that particular functionality. The other way of defining circuit is writing some logical expressions. Maybe in this case I am writing the same problem statement, I am writing in the forms of logical expressions. So yes is equal to a bar b plus b bar a, that is nothing but a XOR b, because we know the expression for the given circuit. Okay, and carry output is equal to a dot b. So this is another way of specifying your design. So after looking at these expressions, one should be able to design this black box. The other way is specifying the relationship between input and output. Okay, so how can it be done? There can be two different possibilities. It may be truth table, in which A, B, C inputs are A and B are the inputs, and sum and carry is the output. So for a given bit pattern, what is the output? So corresponding to every column vector, we have to write one expression. Okay, so from this relationship, input and output relationship, we should be able to design the given black box. Sometimes it also happens that the customers will give you waveforms. Sir, I don't know, but we want to generate the functionality in this way. This is the input and these are the expected output. Now, how would you like to design black box? It is your choice. So there are different ways of design specifications which are provided to design engineer. Okay, so at the end of the course, I am feeling that you are going to be a digital design engineer. Okay, and given this kind of information, you should be able to design the black box, and that is how this book will is prepared, and I'm trying to make you as a digital design engineer. Okay, so now let us say what happens further. So we do have different design implementation methods. We have already seen SOP, POS, and different ways of synthesizing the circuit. Okay, so now once the circuit is given, maybe expression or is given, or it can be truth table, or it can be waveform or word problem. You have designed some circuit. Okay, so from the given expression directly, if we write a bar b plus b bar a, and c is equal to a dot c, a dot b, then the circuit requirement is little different, right? So If you look at the number of stages, here there are, I am assuming inverter input is not available. Inverted input is not available. Usually that is not the case. Usually we assume that inverter inputs are also available. Okay. So if we assume inverted inputs are available, then there are two logic levels. Otherwise, there are three logic levels. Okay. But if you write the expression logically optimize using XOR, then we can directly replace this AND or invert circuit by using XOR. A XOR B is nothing but yes output, and A dot B is nothing but C output. So one XOR gate and one AND gate is required. And if you look at the number of stages in the circuit, there are two only. So how is it going to affect us? If you look at the requirement of the number of ICs here, there are three different types of ICs required in the first solution. One is inverter, the other is AND gate IC, and third one is OR gate IC. So three different ICs. Even if you take 14 pitch package, you need three times space. If you look at this implementation, there are only two logic gates, logic ICs required. One for XOR, one for AND gate. So at least one space required for one hexa inverter you can reduce is number one. Number two, if you look at the number of logic levels, here if I don't assume inverted inputs are available, then there are three stages. So if every gate is operating, let's say at hypothetical value 1 nanosecond, then output will be available here. Some output will be available after 3 nanoseconds, whereas carry output is available at 1 nanosecond. And if I assume 1 nanosecond delay in this case also, the second solution, the output will be available within 1 nanosecond itself. So if we look at the trade-off, the first circuit requires 3 nanoseconds to produce sum, whereas the second circuit requires 1 nanoseconds to produce the sum. Okay. So depending on our area, power requirement, we need to play with the design implementation methodologies. Okay. So many other solutions are there. Let's see the other possibility. So in this circuit, I am showing XOR gate is implemented using NAND gates. Now again, what is the scene here? XOR is converted into NAND gate. So we can do it using simply De Morgan's application, and we know we can convert any circuit into NAND technology. Okay. So if you will look the output expression for sum, there are three stages. First stage is NAND of A and B together. Then second stage, output of the first stage is inverted, and the third stage. So in this case also, there are three time units required for the sum to be made available at the output. Whereas carry output is available immediately after first time unit. Okay. So what is the gain in this? In this case, only one type of circuit IC is required. We don't need AND gate, XOR gate, inverter IC. Only NAND gate IC is required. And since in one NAND gate there are four NAND inverters, we need two NAND gate ICs. So in nutshell, I am showing here the trade-off, solutions and number of gates. So solution 1, 2, 3, and number of gates required in the first case is 6, then 2, then 5, and type of ICs I have mentioned here, all the information in tabular format, and number of ICs, and logic levels I am writing here asterisk, stating that, thinking that inverted inputs are available. So if inverted input is available, sum is available after 2 time units and carry is available after 1 time unit. Okay. So we need to look at this requirement meticulously when we will be doing digital implementation for high speed circuit, high speed low power designs. Okay. There exist other solutions also. Let's say multiplexer based design, there can be decoder based design, there can be solution proposed using memory based design, or there can be programmable logic devices one can use, maybe PAL, PLA, GAL, CPLD. Okay. And depending on our requirement, we should be able to design the circuit. Okay. So what is another perspective which one has to understand while learning this basic course is that scalability of our given circuit. Okay, so in general I am discussing here half adder. The half adder can be converted into full adder. Full adder can be again, four such sets can be used to generate a nibble adder, then byte adder, then maybe word adder, and whatever number of bits you would like to add. So a half adder circuit can be configured or can be connected in this way to generate a full adder. Okay, so first half adder is producing the output, some output which is connected to the A input of the next half adder. The C in input of the from the external world is directly connected to the B input of the second half adder, and carry may be produced by either first half adder or second half adder. So there is a ORing function. Okay, and in short I have shown the symbol of half adder in this downside block, small block, full adder. Okay, and then we can use this full adder block to cascade it n number of times to generate n number of bits addition. Okay, so such scalability we need to look at in the first stage itself. While designing any digital circuit, is my circuit scalable? If not, is it possible, or is there requirement how to do it? So all this thought process has to be started when you are studying this course. Then only you will be very easily able to design the required circuit. Okay, for high speed or low power requirement depending on your logic requirement. Then thinking about a little bit about scale of integration. So everyone knows today the world is talking about ultra large scale integration, but it started with small scale integration, then medium scale integration, large scale integration. So this scale of integration depends on number of gates per IC. So within one IC, how many gates are available? Okay. So if it is less than 10, then it is a small scale integration. Your basic gates like logic gates, AND gate, OR gate, these are falling under this small scale integration. Medium scale integration, if the logic gets in a particular ICR from 10 to 100, then we call it as a MSI integration. Okay, it's medium scale. Such ICs are nothing but some flip-flops, adders, code converters, counters, etc. fall under this medium scale integration. When the number of logic gates are in the range of 100 to 10,000, we call it as a large scale integration. So small size of memories. So if you look at the large scale integration, the first device was 1 bit, 1 kilobits of memory. Okay, wherein roughly 10,000 gates, 9,700 something like gates were integrated. So 1 kilobit memory was the first device which was considered as a large scale integration. It was very early, maybe in 70s, decade of 70s. Okay, then VLSI came into picture. So when the device integration has gone up from 10,000 to 1 lakh transistors or gates per IC, then it is called as a large scale integration. Usually large size of memory chips, maybe more than 1 kilobit, that is kilobytes, you can say 1 KB and so on, or display controllers, etc. fall under VLSI. But if the number of logic gates are more than 1 lakh, we call it as, nowadays we call it as a ultra large scale integration. So typically microprocessors, FPGAs, video codecs, etc. all the sophisticated devices or ICs, whatever we are thinking, DSP processors are all fall under this ultra large scale integration. Okay. Now I'm just giving you in brief summary. Okay. So if at all you want to do such kind of integration, what are the ways? So we need to look at the digital design flow. So we have seen there will be some idea, basic specifications. I want to do this, or implement so and so. So somewhere from somehow you have got some idea. Now you need to look at its functionality. How is it working? You have to you have to go ahead little more and find out the different working blocks. To achieve this functionality, what are the design blocks are required? How can I implement this functionality? So then you will be able to understand what is its functionality in depth. Okay. And then you will start simulating it. So you need to simulate the circuit from functionality point of view. Am I able to achieve my functionality? Yes or no? If no, where am I going wrong? And you need to find out the methodology to implement the given function. But once the function is possible to implement, then you need to look at the HDL. How do I code it? Because your aim is to come up with some silicon chip. So hardware design description languages are meant for that. So you will be doing is HDL coding. It may be using Verilog or it can be using VHDL, whatever language is included in your syllabus. In our book, both languages are covered. Okay. So depending on the HDL, you need to functionality, you need to write the code and then simulate it. So after writing the code, you need to simulate and test the code functionality of your code. Either it is working, the design circuit or design code is working, meeting your functionality or not. If not, you need to revisit your HDL code. If it is meeting, then you will go ahead with synthesis step. So in synthesis step, what happens? You will be trying to implement the circuit in terms of logic gates, and you will be able to understand either the circuit is synthesizable or not. If circuit is not synthesizable, you cannot port, you cannot migrate your design on a silicon chip. So you need to revisit your HDL code in that case. Because if at the end, if you are unable to synthesize your design and put it on the silicon, then you are not going to meet the functionality. So you need to revisit your HDL code and start thinking, where am I going to missing the bus? Okay, and you need to recover from that state. And once the synthesis is available, done, then we do have two different possibilities. It can be ASIC implementation or it can be FPGA implementation. Okay, so if it is a ASIC implementation, we will be moving forward and we will be doing transistor level design, and we need to now connect the transistors from one end to another end. So maybe source drain connections, all of all transistors, how the transistors will be mapped and everything. So floor planning and all. So layout, once layout is ready and if it passes all the design rules, then we can go ahead for fabrication of a chip. And once the chip is fabricated, then you can bring it back to your lab and you can test it and you can check its functionality. Whatever you started with, is it attaining, yes or no? If yes, then is the requirement of power is met, yes or no? Because simulation result and practical implementations results, there will be little deviation. So you can think from that perspective, and if you are not meeting the requirement, you need to revisit. Okay, maybe that can be a second version of your design. Okay, so I was talking about HDL, and there are two types of HDLs which are covered in this book. One is VHDL, other is Verilog. Different universities and institutes are using different languages, either VHDL or Verilog, but primarily both are meant for implementing a given circuit in on silicon. Okay, but there are some pros and cons. The main differences are VHDL is not case sensitive. Okay, you can write capital, small, whatever words you would like, and it will not differentiate between your keywords or identifiers. Okay, but Verilog is case sensitive. So if you miss capital, small, then Verilog is going to create some error messages. VHDL is difficult to run because it is based on Pascal and Ada, and there is a structured methodology. It is strongly typed. So if you miss a particular library to be included, or if you miss the data type conversion, you are going to get, for a single mistake you are going to get 10 numbers of error messages. So sometimes when you are starting as a novice user, your error message is bigger than your code, and then you start shaking and you feel that it is too tough. Okay, and you start giving up. So what I feel is that Verilog is very easy in that sense, because it is based on C, and everyone knows C. So if you know C, the constructs are known to you, main constructs, how to use them. And since it is not strongly typed, even if you do not do type conversion, etc., etc., it is not going to give you issue. Okay, but once your design is ready, and once you have understood the concepts like concurrency or RTL coding, then it will be very easy to migrate from Verilog to VHDL. Okay, so uh, at least at our institute, we start with Verilog and then we go ahead with VHDL, and then we leave it up to the students to dig up it further. Okay, because one should not get at a time. You should not introduce n number of concepts, library, then package, and all. Okay, so you first let the students understand what is the concept of concurrency, what is synthesis, what is non-synthesis, uh, how to write test bench. Once they are compatible with HDL, then you can go ahead with, "Acha, you learned this, but these are the things which are not there in VHDL and Verilog, and how to design it." Okay, so that is choice of your board of studies. I don't have to say anything about it. But moving forward, in both HDL, there are different design abstraction levels. Now, design abstraction levels, typically we can categorize into four. One is behavioral or algorithmic level. We can, in short, say that it is very high level of circuit abstraction, and the code looks like C program. If this, do this. If not, do this. If this is this, etc. Okay, so you will write if else, etc., and then you will be able to meet the functionality. So as a HDL coding engineer, our aim is not to write code like C, right? But to map the circuit or algorithm on a silicon chip. So behavioral or algorithmic level is meant for faster productivity. Then the second level of abstraction is data flow level abstraction. So it is also known as register transfer level modeling, RTL coding. Okay. So here designer has rough idea about its his or her design. What are the blocks? How they are going to talk to each other, how are the interfacing, how is the interfacing between different blocks. Okay, and you start doing block level analysis and block level implementation. So the flow of signals is known to you. So this signal is generated in the input block, output of this block are connected to input of this block, and so on. Okay, so you should know basic data flow of your code. It may not be inner details are known to you, but top level rough idea. Okay, then gate level modeling. In gate level modeling, what happens, you, it is also known as structural modeling. You know each and every bit of your design in this case. So the connection of OR gate is made to the NAND gate. Next, this to this NAND gate there are so many inputs. The output of NAND gate is connected to this. Then an AND gate or NAND gate switches in this way. This is how it is going to happen. Okay, so design engineer has a clear cut idea about the hardware. Okay, but the problem is productivity is low. Now we have just seen that millions of gates are available, and millions of gates you cannot write sitting like one gate to another gate connectivity. Okay, it will not help. Okay, so that is why HDLs have come into play. Okay, and the lowest level of modeling is switch level modeling. So here you are trying to do transistor level modeling. So you are not sticking to gate level. you are trying to implement a given gate using transistor. But this is meant for design cell library development, because the transistors gates are built by using transistors, and somebody will build you this library and you will be using this library to synthesis your circuits. Okay, so it is very difficult for a design engineer to change the change this library, and as the technology node changes, we need one has to design entire library again. So it is not meant for we people to do it fast designs, complete the design cycle faster. So in summarizing, what I have given here is a small Verilog code. The piece of hardware which we have seen, half adder, can be mentioned in Verilog coding in this way. Okay, module, where the module is just keyword. So all the keywords are highlighted in blue. Okay, and then the name of your module and the connection ports, in ports interface port, sum, carry, A, B, whatever are the on the periphery of your design. Okay, then you are doing this XOR and AND operation to generate the sum and carry output, and then you will write end module. So in general, your file starts with end and termination is with end module. Okay, so this is generalized structure of your Verilog code. But now here the XOR and these are the, so here I know the connection, how A is connected, B is connected, and how the outputs sum and carry is connected. And if I do coding in this way, it is called as a structural coding or gate level coding. So second last design abstraction level. Now, if I replace these two lines, XOR and lines, by just statement like shown in the lower box, assign S is equal to A XOR B, and the second statement is assign C is equal to A and B. So this is also going to create the same hardware, whatever we have written. But the second portion, second block, whatever is written here, you can call it as a data flow. Here I know what is the operation which is taking place on the input literals A and B, and how they are processed to produce the output sum and carry. Okay, so this is how one can, so from the perspective of design engineer, this is a very good methodology to write, because you can quickly finish the design and move ahead. Okay, now when it comes to HDL, this is the first place where the students will get confused. The language HDL consists of two sets of constructs, synthesizable construct and non-synthesizable construct. If you do not introduce this to them, they will be really in soup. Okay. Synthesizable constructs are the constructs which are used to design your module and to port your design on the silicon, whereas non-synthesizable are meant for testing your design. So one set of statements can be used in test bench also, the other cannot be used in design, because it is meant for testing the circuit. And when you are in teaching the synthesizable constructs, you need to tell them very nicely what are the two different categories of synthesizable constructs. One is concurrent construct and other is sequential constructs. Okay, so one cannot use concurrent statements to write model the sequential circuits, but one can use sequential constructs to model combinational as well as sequential circuits. So if we do not introduce them this point to the students, they will always be in confusion. So all these points are very nicely covered in the revised book. And this is how the test bench will look like. Your Verilog test bench, which is a wrapper to your design under unit or unit under test. So you will be forcing the stimuli from the test bench to the inputs. The data will be processed by the circuit, whatever you have implemented, and the outputs will be generated at the output data. This output will be acquired by the tool, and then it will be displayed on the screen, maybe in the terms of waveforms, or it may be in terms of text pattern, whatever you program. Okay, so this is how the test bench can be written. So for the given code, HDL code, I have written the test bench for the half adder here. So again, as I stated, module and end module is the framework wherein your all the set of constructs are going to reside. So initial is nothing but initialization of your signals, and pound 100 is nothing but after how much delay you want to toggle the signals. So A is equal to 0, B is equal to 0 at 0 time instance. After 100 time instance, you want to change A to B to 1. So after hash pound, B is equal to 1 tick B1. So its language construct is mentioned in that. So I have to write it in that way. And B is raised to 1 and so on. So if you write in this way, your design, you will be able to test, and corresponding to this waveform, now some waveform will be generated at the output yes and C, that is sum and carry. And you can cross check either you are meeting the design functionality, yes or no. And it is so simple to write code in Verilog. And if you are working with VHDL, you need to include library. Then either it is a Boolean operator or bitwise bit operator, type conversion, etc., etc. You have to involve everything, and then only the students will be able to write the piece of code. So let it be simple, make it simple for them to digest and understand. And at the end of the course, they should be able to design at least circuit with hundreds of gates. And from that perspective, I have introduced mini projects at the end of the book, whose complete solution is given on the online contents, which are accessible to faculty members. You can download the presentations or codes from there, and you can the codes whatever are given in the book. You if you edit it as it is, the codes will work, and their waveforms, test benches, everything is given. You need to simply copy the code and paste it, and it will function. So, as a beginner, as a novice user, you need not to worry too much. You can start reading the book, and you can understand the concept at any instance of time. If you feel we are facing problem, you can write to me. My mail ID is available on my web page as well as on the in the book also. Okay, so feel free to contact me, and I can take up questions now. Okay. So what is a driver? This is a question by Gaurav Agrawal. Driver is nothing but the output. Let's say, be simple. When I turn on a switch, okay, maybe a tube light or a fan at your home. When you turn on, as long as the switch is turned on, 230 volt is reaching to that tube light or fan, and hence the lamp is lighting up or fan is rotating. The moment you turn it off, there is no one to drive that fan or tube light. So is the case. As long as some transistor is driving the output, the circuit will generate the output. Otherwise, no. Okay. Then the second question is, what are the applications of modern digital electronics? Oh, there are a number of. You take any digital gadget, you can start from your digital smart TV to mobile smartphone to smart uh, car. Okay, everything is digitized now. So, but remember that none of these designs include block which is not taught to you in your basic digital circuit course. The same blocks are there. You need to rearrange them to meet the functionality. Everybody has learned number system, AND gates, OR gates, mux, demux, etc., etc., and then they have become design engineers and they are designing VLSI chips. They also started some time down the line, like you as a graduate engineer. Okay, so don't worry what are the applications and how we are going to do it. You study the fundamental course very carefully, and you will be there down the line after 4 years. Okay. Transistors are made from, okay, Kaushik is asking transistors are made from what? So transistors, see, there are now different technologies. We can have silicon based transistors or germanium, or it can be nowadays we are thinking about uh, polymers, right? Different polymers. Wherever we are thinking of flexible electronics, then the transistors are implemented using separate low temperature processes are used to fabricate the transistors. So this question you will be able to understand more once you read the VLSI technology course, and the other course is basic electronics engineering course. So from that you will be able to understand the concepts. Okay. So Dr. Ravindranathan is asking, is should we limit ourselves learning to Verilog alone? In my opinion, we should learn Verilog, understand how the simulators are working, what is synthesis, what is meant by synthesizable construct, non-synthesizable construct, test bench writing. Once are very well versed with the tool and concepts are known to us, then we should introduce HDL, VHDL to the students. Okay, because the when we are starting VHDL, we are starting with library, use IEEE. And if the context is not known, the students won't be able to write the code for the unknown designs. Okay, because they don't have what a library is, what package is, how to convert the signals. They will be confused, either they are writing incorrect code, or the language is unknown to them, so they cannot build confidence. Let them build. Our As a teacher, we should build their confidence, and then we should put them in the complicated situation. Okay, so initially teach Verilog, and then we can go ahead with VHDL. Okay, that's what I follow. Okay. Then Kaushik is asking about what is difference between test bench code and actual code in the Verilog, sir. Okay. If you look at the test bench code, I'll go back here. Here on the one side there is a Verilog code which is synthesizable, and on the right hand side of your screen you are seeing the test bench code. So if you look at the test bench code, I am writing pound sign with hundreds, right? So 100 is nothing but time delay. On time, on synthesis tool, or when we are working with silicon chip, it is not possible for us to hold on the signal for 100 nanoseconds, right? We cannot. The only way to do that is to pass it through a flip-flop or registers, or pass it to the uh, chain of inverters, or fabricate a delay line and then delay the signal. So what I am trying to say is that delays are not synthesizable. If delays are not synthesizable, and if the non-synthesizable construct is not given to me, how do I test my circuit? Either it is going to respond to the signal which is changing after 100 nanoseconds. So from that perspective, non-synthesizable codes have been introduced. So your test bench can include any synthesizable or non-synthesizable code. But if you want the circuit to be mapped on silicon, we should use only synthesizable constructs. I hope I have answered your query. If you are not clear about this, you can revert me in mail. Okay. Is there any other question? Do we have any Indian IC or microcontroller manufacturers in India? Yes, recently we have IIT Bombay has launched Ajit processor, and IIT Madras has also launched two processors, right? As a manufacturer, okay, silicon fabrication capacity, we do have SCL Chandigarh, but the very technology is very old. It is 180 nanometer, whereas the commercial technology node is at 8 nanometer. Okay, and rest of the things other than fabrication, up to physical layout or physical design, right from the design specification to uh, transistor level modeling of the IC is done in India. We do have that capacity, and lot of corporate offices are doing this. All Intel, Xilinx, AMD, uh, Qualcomm, NXP, uh, or you you take big names, all are doing some kind of chip development. ARM is also doing intellectual property level in designs in India. So there are huge opportunities in digital hardware engineering. Okay, you need to have basic fundamental concepts very carefully done. Then you can do it. Okay. Any other question?
Hello, sir. Kishore, sir.
Yeah. Yes.
Yes, sir. Yeah, I think now we can end this session. If they have any more questions, I will share your email ID with all the attendees.
Sure. Sure.
And this is to
Sure. Thank
inform,
you.
yeah, yes, sir. And this is to inform all the attendees that you will be receiving a participation certificate from McGraw Hill, India, signed by our managing director and Kishore sir as well by tomorrow or day after tomorrow. If you have any other questions, uh, you can write us, or you must have received a reminder from McGraw Hill WhatsApp channel. There also you can put the query, or you will be also getting sir's mail ID directly by tomorrow or day after tomorrow with the certificate. Thank you everyone who has attended. Thank you, Kishore sir.
Thank you very much for listening to me so patiently, and I hope you will grab your copy very soon. Thank you.
Yes. Thank you. Thank you. We are ending the session now.